Hello, everyone, and welcome back to another lecture for the Transitions to Advanced Mathematics course. In the previous lecture, we talked about the completeness of the real numbers and what that actually means, and how even though both the real numbers and the rational numbers are ordered fields, only the real numbers can be considered as complete ordered fields because of you know some of the properties we discussed in section 7.1. So now we're going to move on to 7.2, and it's a big section because it thinks about some of the properties of the real numbers and establishes some properties of the real numbers, and we get to one of our first major theorems of analysis. It is a big section, and so I'm splitting it up into two parts. And so this first part you can think of as being some topology of the real numbers. We're going to just basically introduce a lot of terminology, and then in part two, we'll introduce some more terminology, in particular regarding compactness as it relates to the real numbers. And then we'll establish and prove the Heine-Borel Theorem. Okay, so we're going to talk about today some topology of the real numbers. And so, again, we're going to work our way, we're going to establish some results and work our way towards establishing the Heine-Borel Theorem. And so we're going to establish some definitions and some theorems, and we're going to apply them to the real numbers, but they can apply more generally to any complete ordered field. So let me just write that down. Results here apply to any complete ordered field. But we will focus on the real numbers. Okay, and so we're going to immediately jump into a definition because that's what we do. So let's start off with the definition here. And this is just a tool, a definition, a structure we're going to use to define more characteristics. So let A and delta be real numbers with delta positive. Okay. The delta neighborhood of A is the set, and then you write this fancy schmancy n. So this is the notation for the delta neighborhood of A. And what is this set? This is the set of real numbers such that the absolute value of x minus A is less than delta. Okay. So it's a simple structure, but we can build several characteristics of the real numbers with this notation. So the delta neighborhood of A consists of all points whose distance from A is less than delta. Okay, so for example, let's use colors here because I'm kind of bored. Let's consider, n of 3.4, and then let's also consider, say, n of 1 and 0.01. Okay, so this is going to be really the open interval from from 0.99 to 1.01, and the top is going to be the open interval from 2.6 up to 3.4. And you can draw this quite easily on a number line, right? So if this was a number line, say 1 is here, 2 is here, 3 is here, where is the red delta neighborhood? Well, it's centered at 3, and it goes from about 2.6 to about 3.4. So that's n of 3 and 0.4. And where's the other one? It's just right up against 1 here. So it's called a neighborhood because you can measure closeness with other points with respect to these neighborhoods. So for example, we won't cover this in this class, but for example, a function f, a real valued function with whose domain is the real numbers, is continuous at a point A in its domain if and only if for all epsilon greater than 0, there exists a delta greater than 0 such that if x minus a is less than delta, then the absolute value of f of x minus f of a is less than epsilon. So as you make x closer to a, f of x gets closer to f of a. And this is sort of the classical definition of continuity. But you can rewrite this in terms of neighborhoods. So you can write a function f is continuous at a point a in its domain, right? So alternatively, you have a function f is continuous at a point a in its domain if and only if for all epsilon greater than 0, there exists a delta greater than 0 such that if x is in the delta neighborhood of a, then f of x is in the epsilon neighborhood of f of a. So it's a nice way to think about characterizing different properties that you sort of take for granted or it's already in your brain. Really, when you think about continuity, you're thinking about closeness, and so instead of thinking of distances when you think about continuity or things like that, or even when you're thinking about limits of a sequence, instead of thinking about how far is the sequence from a particular limit, you can think about what set encompasses the terms of a sequence and how big is that set. And so you can think of things in terms of neighborhoods instead of distances, such as an absolute value. Yeah. Okay, so that we talked about neighborhood. So let's move on to another definition now. For a set A that is a subset of the real numbers, a point X is an interior point of the set A if and only if there exists a delta greater than 0 such that the delta neighborhood of X is a subset of A. So we say a point of a set is an interior point to that set if you can find some radius such that that neighborhood is still contained within the set. In particular, when you construct that neighborhood with whatever delta you can, all the points in those delta neighborhoods, all the points in that delta neighborhood are going to be inside of A. Okay, so when you construct a delta neighborhood of an interior point, so you can construct a delta neighborhood of an interior point such that all the points in that neighborhood are also inside the broader set. Okay. So, example. Consider the half-closed interval 2, 5. 3 is an interior point. Why? Because if I set delta equal to, say, 0.1, the point 0.1 neighborhood of 3, which equals what? That equals 2. That equals 2.9 to 3.1 is a subset of 2, 5. Right? And indeed, every point in the open interval 2, 5 is an interior point of the bigger interval, closed interval 2, 5. And this again has to do with the properties of an ordered field. There's no real number that's just immediately to the left of 5 or immediately to the right of 2, right? And so any number in this open interval 2, 5 is going to be a point interior to the half-closed interval 2, 5. The point 2 is not an interior point. No matter what I choose delta to be, the delta neighborhood around 2 will not be a subset of 2, 5. Okay, So just to get you oriented, let's look at this on the real line. So we're looking at the interval from 2 to 5. And remember, the claim is that any number in this open interval is going to be an interior point. So any number in this open interval I drew is going to be an interior point. So 3 we showed clearly is an interior point because I can draw a nice interval around 3. 4 is an interior point. Whatever this number is right here is an interior point. And you might be curious, well, what if I get really, really, really close to 5 or 2? Like, let's say I get really, really, really close to 5, right? So, like, I've gotten 5 right here, and I choose, like, the point right here. Is that still an interior point? Yes, no matter how close you get, I can still draw some parentheses around that point. There's still some space there for which I can make sure that the neighborhood is contained within the interval, right? And the same is true for the other side. I can get arbitrarily close to 2, and all those points are going to be interior points. However, if I choose 2, so if I choose the point 2, no matter how small I draw the parenthesis around 2, i.e. no matter how small I take delta, there are going to be some points that are outside of my interval. And so 2 is not an interior point to the interval, to the half-open interval 2, 5. Okay. So next definition. The set A, which we take to be a subset of the real numbers, is called open if and only if every point of A is an interior point. Of A. The set A is closed if and only if its complement, so denoted AC, is open. Okay. So yeah. So just some examples. 2, 5 is an open set because every point in this set is an interior point. Therefore, the complement of this set, which is negative infinity to 2 union 5 to infinity inclusive, this is a closed set. Right? Sorry, keep messing up here. The interval we just discussed in the previous example is not open because 2 is not an interior point, but 2 is an element, 2, 5. But is this a closed set? Well, we're going to look at the complement here. And if the complement is open, we can say that it's a closed set. But notice the complement has a similar property. This is also not an open set. Because 5 is not an interior point. But 5 is an element of this interval. So this set 2, 5 with the side on 2 closed is neither an open interval nor a closed interval. So as opposed to, doors or eyes or something, a set need not be either open or closed. In some cases, it can be neither. So here's another interesting example. R is an open set. And to do that, you just look at every real number and can you construct a neighborhood of that real number that is still containing the real numbers. And if you just think about it for like 1 second, you'll say, of course, yeah, you can. And it's not for any radius, it's just for some radius. You have to be able to do it for some radius. So R is an open set because for all x in R, you just give the radius 1 is still a subset of R, right? Now, interestingly, the empty set is an open set. Just because by a vacuous argument, there's nothing in it, and so I can clearly construct a neighborhood of nothing and still say that that's a subset, because I'm talking nonsense. And so just by this nonsensical argument, you can just say that the empty set is an open set. A logician would think about this and say, why is this an open set? Remember, to characterize it as an open set, you have to say for all x in the set, there needs to be a neighborhood of those elements that is still contained in the set, but there are no elements, so the antecedent is false. And this goes back to logic in way back in chapter 1, where if the antecedent is false, the conditional statement is already true. So this is interesting, but notice that the real numbers and the empty set are complements of each other. So the real numbers is also a closed set. And the empty set is also a closed set. So not only do we have sets that are neither open nor closed, we have sets that are both open and closed. And in the real numbers, at least, these are the only 2 examples of the sets that are both open and closed. And you can prove that. We're not going to do that in this class, but it's more sophisticated. It's a more sophisticated proof. So these are the only sets satisfying this. For R. And what this corresponds to is R being connected. Again, that's just a fun fact. If you don't care about this, you don't need to know about it, but if you're interested in these types of things, connectedness is an important property. And so what this example basically says, or not the example, but the idea that these are the only sets that are both open and closed, says that R is connected. So yeah. So let's go on to this theorem. Before we go on to the theorem, so yeah, just to reiterate, a set is open if about each element in the set there's a delta neighborhood that lies entirely within the set. And what this means is, in principle, what this means is that no point of the set can be on a boundary or on the outer edges. And so let's look at some theorems that will help us recognize some open sets in the real numbers. Every open interval of real numbers is an open set. Okay? So if we can prove this, this makes it really easy to know whenever, well, in particular situations when a subset of the real numbers is an open set. So let AB be an open interval with AB a subset of the real numbers, right? It's just an open interval. And we're going to take an arbitrary element in that open interval. And what do we need to do? So we need to show X is interior to AB. That is, we need to be able to find the delta such that the neighborhood of X around the neighborhood around X of radius delta is still contained in AB. So we need to show there exists a delta greater than 0 such that the delta neighborhood of X is a subset of AB, right? So set delta equal to the minimum of X minus A and B minus X. Then delta is positive, right? To show that the delta neighborhood of X is a subset of AB, let Y be an element of this delta neighborhood of X. Then A, which is, I'm going to do some fancy schmancy work here, but this is X minus A, is less than or equal to X minus A is less than or equal to X minus delta, because if X minus A is the minimum, that's going to be equal to delta. But if X minus A is bigger than B minus X, then this quantity on the left here is going to be smaller than whatever you subtract, right? So, okay, so yeah, so A is equal to X minus A, and X minus A could very well be delta if it's the smaller of X minus A and B minus X, But if b minus x is smaller, that means you've taken away a bigger quantity um, than delta. And so this inequality holds, which is less than x minus delta, which is going to be less than y. Why? Because y is in that neighborhood, which is less than x plus delta, right? Which is going to be less than or equal to x plus b minus x, which again, if delta equals b minus x, then that clearly holds. But if delta is equal to x minus a, that means you've added a bigger quantity, b minus x. So it's less than or equal to b minus x, which equals b. So y is in the open interval ab. And so that proves it. Okay, so straightforward, I think. Just to get you acclimated to some more tools and types of proofs we write in analysis. Okay, this is going to be a fancy schmancy A. Something like this. Let fancy schmancy A be a non-empty collection of open subsets of the real numbers. Then we have the following two results that hold. The union over all the sets in that fancy schmancy collection of A is an open set. And secondly, if oh, that's horrible. That's horrible. Don't know how they write this A, but okay. If A is finite, and we'll see that this is important, if A is finite, then the intersection over all the sets in that fancy schmancy set collection is an open set. Okay, so let's prove this. So proof. So first we're going to prove part A, which says that if I have a collection of open sets and I take the union of all of them, then the union is still an open set. So suppose X is an element of that union. Right? Since X is in the union over the collection, of open sets, there exists a set B in that collection. Jesus. Gosh, sorry. Okay, there exists a B in that collection with X belonging to B. Since B is open, X is interior to B, meaning there exists a delta greater than 0 with the delta neighborhood of X being a subset of B. Since B is a subset of the union over the sets in that collection, it follows that the delta neighborhood of X is also a subset of that union. And that completes the proof. Okay, because I found a delta for every point in that union such that the delta neighborhood of every point is contained within the union. So the collection of the union of open sets is open. B. So suppose this fancy schmancy set is finite. So you're looking at a finite number of open sets now, and say X is in the intersection over all the sets in this collection. Then X is an element of A for all A in that collection, right? So for each open set A, and just let me remind you, A is a non-empty collection of open subsets of R. Okay, so each A in the collection is an open set. So for each open set A, there exists a delta sub A greater than 0 with the delta A neighborhood of X being contained within that A. Now we define delta to be the minimum of all those delta A's, with A being taken from that fancy schmancy collection. Then delta is greater than 0, and the delta neighborhood of X is then going to be a subset of the delta A neighborhood, which is going to be a subset of A for all A in the fancy schmancy collection. Thus, the delta neighborhood of X is going to be a subset of the intersection. So X is interior to the intersection. And so that proves that the intersection of a finite collection of open sets is also open. And for part B, the finiteness is absolutely paramount, because you can always find the minimum of a finite set of real numbers. If you have a finite set of real numbers, you can always find the minimum. And whenever we, let me just go back to the proof here. Notice I said let delta be the minimum of delta A for all A in this collection of sets A. If that collection is infinite, there's no guarantee that I can find that the minimum of that collection is going to be positive. right? But because it is finite in this case, we are able to find it. And so it's paramount that we specify that it's finite. If that set were infinite, we can't be sure of finding a minimum that's positive. So if delta A with A taken from, so if this set is infinite, proof doesn't work. So, for example, say your delta A's, say your collection of sets is just a collection 1 over n such that n is taken from the natural numbers. So now your set is infinite. What is the minimum? Well, in particular, there is no minimum. And so you wouldn't be able to just say let delta be the minimum of this set because the minimum does not exist. And so the theorem is false if we omit the word finite. Okay. Okay, so some more examples now. So just some examples pertaining to the theorem we just talked about. Consider let's say sorry, there we go. So consider the family of intervals a sub n, which is going to be equal to 2 minus 1 over n up to 5, which is a subset of the real numbers, with n taken from the natural numbers. And so now you're taking an intersection over, now all of these intervals, all these a sub n's are open intervals, but now you're taking the intersection over an infinite set of a sub n equals our good old friend, the half-closed interval 2 to 5, which is not open. So this is just an example showing how if your set is infinite, and then if you have an infinite set of open intervals or open sets, and you try to, take the intersection over them all, you might not end up with an open set. Yeah. So some more examples. You can use the theorem we just talked about in order to create many sets, right? So many open sets. So for example, 5, 7 union minus 3, 4 union 10, 20 is open. And I know this just off the top because I've taken the union over 3 open sets, and I know that the union of any number of open sets is going to be open. Yeah. Also, for example, if you take the real numbers and just puncture it, so this is just the following. This is also open. But you can also characterize other sets, right? Like 2 to infinity is open. Because 2 to infinity equals the union for x greater than 2 of open sets 2 to x, right? And so you can clearly show that 2 infinity is an open set. So corresponding to this, you can show that every closed interval of real numbers is a closed set. Okay. Yeah. So every finite subset of R is closed. Every finite subset of R is closed because the complement of a finite set is the union of 2 open rays, right? So finite sets are good examples of sets that are both closed and bounded. Okay, so let me just write down what I'm saying. It kind of sounds like I'm kind of going awry here, but so now let's just write this important fact. Every finite subset of R every finite subset of R is closed because its complement is what? Its complement is the union of 2 open rays and a number of open intervals. So finite sets are good examples of sets that are both closed and bounded. So finite sets are good examples of sets that are closed and bounded. So remember what it means for a set to be bounded. We've talked about it quite a bit. So yeah. So closed and bounded sets have a very interesting property, and let's look at that by looking at the following theorem. If A is a non-empty, closed, and bounded subset of R, then sup of A is an element of A, and inf of A is an element of A. And we're going to prove this, but I'm only going to prove it for the supremum, because the proof for the infimum is exactly the same. So this is a cool result. So we saw several examples of sets whose supremum were not elements of that set. Most notably, the set of rational numbers whose squares were less than 2. The supremum of that set was something like the square root of 2, and that's definitely not in that set. But if you have a closed and bounded subset of the real numbers, then the supremum must be an element of that set, and the infimum must be an element of that set. So proof. suppose A is a subset of the real numbers, and A is closed and bounded, right? Let S equal the supremum of that set, and say S is not an element of A. So we're going to use a proof by contradiction. Then S is in the complement of A. Okay, and because A is closed, its complement must be open. So AC is open. Thus, there exists a delta greater than 0 such that the delta neighborhood of S must be contained within that complement. But this means S minus delta is an upper bound for A. Since S minus delta to S plus delta is a subset of AC. This is a contradiction because S is least upper bound. For A. So S must be in A. And again, the proof for the infimum is pretty much exactly the same, but on the other side. And so I'll let you think about how to do it. So yeah, so let's just see some examples of this. So if I let A equal to 5, this is closed and bounded. And notice the supremum of A equals 5, which is an element of A, and the infimum of A equals 2, which is an element of A. B equals minus 2 to 2, union 4 to 10, union the singleton 12. Is closed and bounded. And notice the supremum of B equals 12, which is an element of B, and the infimum of B equals minus 2, which is an element of B. C, so it's going to be another example of a closed and bounded set. So inverse powers of 2 with the powers taken from the natural numbers, union with 0 is closed and bounded. The supremum of C is 1/2. Sorry, for some reason it's not writing. 1/2, which is an element of C. The infimum of C equals 0, which is an element of C. Okay, so last thing. The bounded set, 0, 1, non-inclusive, does not contain its supremum. The closed set, 2 inclusive to infinity, does not have a supremum. And so in order to guarantee that a set contains its supremum and infimum, the set must be closed and bounded. And okay, so this concludes part 1 of the Heine-Borel Theorem section, topological aspects of the real numbers, some topology of the real numbers. We'll continue with this section in the next lecture, so hope you enjoyed it, hope you're learning. All right, so I'll see you in the next lecture. Thanks.